All right, on to 13.3. The last section to be covered has to do with something called z-scores. Now, a z-score is given two different ways, depending on if you're given information about a population or if you're given information about a sample. Most of the time, we're dealing with samples. So if you're given a sample mean, a sample standard deviation, and then you're looking at some value in a data set, the z-score is calculated in this way. You take the value from the data set, you subtract the mean, and you divide by the standard deviation. Now, if you give a little thought to this calculation, what you're doing, the numerator is the difference between the value and the center of the distribution, the mean. And then you're dividing by the standard deviation. So you're taking the difference between a data value and the mean, and then dividing by the standard deviation. So the number that you get for a z-score is going to tell you how many standard deviations that x value is away from the mean. If the z-score is positive, then the data value is going to be above the mean. If the z-score is negative, then the x value, the data value, is below the mean. But it's going to tell you how many standard deviations away from the mean your x value is, your data value. Now, sometimes you might see it like this. Don't be confused by these two different formulas for z-score. It's really the same thing. It's just here we're looking at population data. So instead of x bar being the mean, mu is the mean, because that's the population mean. Remember, way back to our definitions of terms. And sigma is the population standard deviation in place of S. But really, it's the same formula, right? So if you're given population data and an X value from that population, you're going to use this formula, but it's really the same, right? You're subtracting the mean from the data value and dividing by the standard deviations. Both meanings are the same. Your z-score tells you how many standard deviations either above or below the mean your value is, your 1x value that you're looking at. All right, so if we just use this in an example, number 2, we can see in number 2, we're given a sample mean of 212 and a sample standard deviation of 40. And then we're asked to find the z-scores for several different x values. I'm just going to do the first 2 here. The first value is 200. So if we want to find the z-score for 200 in this distribution of values, all we're going to do is use this formula here. So our z-score is going to be the x value minus the mean divided by the standard deviation. And we're going to come out with a number of negative 12 divided by 40. And that is a negative 0.3. So negative 0.3 is going to be our z value. And what that again tells you is that the x value of 200 in a set where the mean is 212 and the standard deviation is 40, a value of 200 is 0.3 standard deviations below, because it's negative, below that mean. And that makes sense, right? 200 is 12 below the mean of 212. 12 out of 40 is going to be 0.3. So 0.3 standard deviations below the mean. For 224, it's very similar. X value of 224 minus the mean of 212 over 40. Notice this is just going to be positive 12 over 40. So that's going to be a positive 0.03. So 224 is 0.3 standard deviations above the mean of that data set, right? So z values, positive above the mean, negative below the mean. So that's how you find z-scores. Now these might be put into a word problem. right? Such as number 8, right? Number 8, let's read it. Number 8 says we're dealing with a random sample of 80 tires, doesn't matter how many, and N doesn't come into our calculations for z-scores. But it says a random sample of 80 tires showed that the mean mileage per tire was 41,700 miles. And the standard deviation was 4,300 miles. So we're given a sample mean, we're given a sample standard deviation. So we're going to use this formula. And it says, what is the z-score? Determine the z-score to the nearest hundredth for a tire that produced 46,300 miles. Of where? Right? So all we're doing is putting this x into this formula with this mean and this standard deviation. So no big deal there. Same as we've been doing. 46,300 minus the mean divided by the standard deviation. And again, we plug that into our calculator. 46,300 minus 41,700 divided by 4,300. And we get 1.07 rounded to the nearest hundredth. So that is the answer to part A. You just take the value given, use the z-score formula. So this tells us again, what does this tell us? This tells us that if our tire lasts 46,300 miles, that is 1.07 standard deviations above the mean of that sample data set. All right. Now, one more thing you should be familiar with here, you might be asked a question such as 8b, where it says, if the z-value is negative 2.44, what does that mean for x? Right? So here we're given the z-value, and we're trying to solve for x. Right? Up until now, we were given an x value, the mean and the standard deviation, and asked to find the z-score. Well, now we are given the z-score and asked to find x. So we're going to take this formula and solve it for x. We're solving for x now. So if we solve this formula for x, well, let's multiply both sides by s. Right? So now we get sz. These s's cancel out, and we're left with x minus x bar. We're solving for x, so we're going to add the sample mean to both sides, right? So if we add the sample mean to both sides, we get the standard deviation times z plus the mean. That's going to be our x. Right? So now we can use that formula to find x. So if we do that with this z, we're going to say the s was 4,300. The z was given to us as negative 2.44. And then we're going to add the mean of 41,700. And when we do that, we'll get the x values. 4,300 times negative 2.44 plus 41,700. And we end up with 31,208 miles. All right, so if we're told that the z value for a certain tire is negative 2.44 standard deviations below the mean, we can take the original z-score formula, solve it for x, plug those numbers in, and get our answer of 31,208 miles. All right, so that is z-scores.